Okay, so we're going to look at section 2.4.3, differential properties of curves. If you think back to the motivational example I was talking about in the previous video, where you have two charged particles and you want to move one in a certain path and work out what the work you have to do is, then one thing you need to know is what direction the particle is travelling in at any point along the curve. So you're interested in tangent vectors to the curve, and when we're trying to measure those things with parameterizations, you need to think about velocity vectors. So that is going to be definition 2.41. So velocity vector of a parameterization. So let gamma be one of these parameterization maps. So it takes some interval of the real numbers into affine n space. Let that be a parameterization of the curve C. Then the velocity vector gamma at the point t0. So if it were t0 is some time here, this is going to be equal to gamma dashed at t0, which is going to be gamma 1 dashed at t0 all the way down to gamma n dashed at t0. So all we're doing here is just taking the coordinates of so the coordinate functions that make up gamma and differentiating each of those with respect to time. And so then we will get the rate of change in the direction x as time increases, rate of change in the direction y, and so on all the way down. Okay, so just to clarify, that means that gamma I of t0 is d of gamma I dt evaluated at t equals t0. Good. Okay, name velocity vector here is inspired by the idea that we have a particle moving through space, and that the I here we're thinking of as being a subset of time. Doesn't have to be, of course, but it tends to be helpful to think about these curves as being traced out in time. So velocity vector is an appropriate name in this situation. We tended to think of vector fields as being fields that exist across the entirety of affine n space for some n, but there's no reason that you shouldn't think about them as being ways of assigning vectors in some other space to points in a subspace of AN. So in the case that we've got a curve here, we end up getting this vector at each point along the curve given by the parameterization, and that vector lives inside AN, or inside the tangent space at AN at each point. But so what you end up doing is creating a vector field here just along the curve. So this isn't a vector field that exists across the whole space, but just along the curve. Right, so let's move on to example 2.4 3, which is just to recap a parameterization that we took of the circle right back at the beginning. So recall the parameterization. So we went from 0 to 2 pi into A2 just in the following way, by taking t and mapping it to a cos t and a sin t. So you can imagine what we're going to do. We're going to just work out what the velocity vectors look like, which we can do by differentiating. So gamma dashed of t is going to be what we get by differentiating at each of these points. Let's write t0 just to be clear that we're going to plug in a fixed t after differentiating. So what do we get? We get, of course, minus a sine t applied to t0, so minus a sine t0 and then a cos t0. So those are our, so that is a velocity vector that we get at the point t0. And you can see that you really do get a point that is tangent to the ambient curve that you're looking at. And if you were to draw this out, and perhaps we'll just take a couple of cases just to make ourselves happy that this is what's going on. So you remember, this is where we started with t is 0 and we hit the point a0. So if I plug t as 0 into this vector, so at 0 I get 0 in the x coordinate, but I get a in the y coordinate. So I've got a vector here of magnitude a pointing directly upwards, and that is indeed, given that the point is going around this way, this vector is tangent to the curve at that point. And if I took, I'll just do one more. Let's take t0 is pi over 4, so that's 45 degrees. I'm going to get a over root 2, and here I'll get minus a over root 2 and a root 2. So I'm going backwards by a over root 2, but upwards by a over root 2. So that's another vector of magnitude a, but going at a point which is, again, sort of tangent to this circle there. Okay. Right, well, what we want to have a think about is how these velocity vectors are going to change with the parameterizations of the curve that we take. So one of the things that we'll find is that the magnitude can change. If you may trace out the same curve, but if you do it at a faster rate at one point and a slower rate later on, then you would expect to get a higher magnitude of velocity at different points. But what will happen is that the direction that you get at that point will always stay the same. So this is our first kind of statement about the invariance of some of the quantities that we're going to look at under reparameterizations. So let's say what we mean by a tangent vector. A tangent vector to C at a point P is a velocity vector gamma dash of t0 such that gamma is a parameterization of C, and P is equal to gamma of T0. Okay, so we are hitting a point P at T0, and then we get a velocity vector from that, and that's going to be all the tangent vectors that we're that's going to be our definition of a tangent vector. So this does mean, in principle, you have to consider all the possible parameterizations of your curve, and in order to get all the possible velocity vectors. Okay, and then the tangent space to C at the point P is just that complete set of tangent vectors. So we're going to write that T P of C, so tangent space at the point P of C is going to be the set of all tangent vectors to C at P. Okay, it is clear that we are getting vectors based at P which are in the ambient n-dimensional space because, well, when you calculate a velocity vector like this, you do indeed get something which is in AN. So it's certainly true that what we get, this tangent space, is something in the ambient n-dimensional space AN. What isn't so obvious is why it should be a subspace of it, or why it should be one-dimensional. But that is in fact true. Okay, so let's, before we go any further, let's do an example. So back to the same place we were before. We're going to let C be the circle of radius A, based at the origin, and we're going to take a point P. That's just going to be the point minus A0. So we are on the left side of the circle. So what we're expecting is that this tangent space ought to be the line that we get going through that point. So let's just see that that is indeed what happens. Right, so we're going to take the parameterization that we had before. So gamma is going to be taking t to a cos t, b a sine t, as before, and we can see that the value of t0 in order to hit this point is going to want to be pi. So this gives us minus A0. So let's use that. Let's use that to work out the velocity vector that we get from this parameterization. If we differentiate, as we have already done in the previous question, we get minus a sine t and a cos t, and then when we plug in pi, so at t equals pi, we then get 0 and a. So that is, sorry, and minus a that should be. So that is indeed a vector going downwards. So let's now think about some reparameterizations which will give us different velocity vectors, and let's see that we can actually piece them together to form a full one-dimensional space. So consider different parameterizations. So gamma tilde, we're going to call them, of C via the reparameterization map phi. So let's say phi takes 0 2 pi over k to 0 2 pi, by just scaling by t. So we take t to k times t. So what we're going to be doing here is we've shortened the interval, so we are so our gamma here, which gamma tilde here, is going to be running k times as fast as gamma round the circle. So what does this do to, so what's gamma going to be defined by? Gamma is going to take t to our original gamma, which is this one here, of phi of t, which is therefore going to be a cos kt and a sine kt. Okay, so we can now differentiate this and get some new velocity vectors. So gamma dashed of, right, now we have to find again the same point, so we want to make sure that we still are getting the left side of the circle, so we still want to get the point minus a and 0, which means that we want to put in here minus, so we want to put in pi over k. Then if I put pi over k in here, then I will get the correct thing. But when I differentiate it, I will get minus a k sine k pi over k, and then a k cos k times pi over k. Okay, and then when you simplify that, you realise that this is just going to be is going to be 0, and this is going to be minus 1. So this is 0 and minus AK. So by choosing k to be any number I like, I can then arrange that I can scale the vector, the velocity vector that I got here, 0 minus a, by any scalar here. So I can get anything I want along the line, which is at that point, tangent to that point.